Okay, so today we're going to go over improper integrals. I know we did this before, but there's a second type, and that is improper integrals with infinite discontinuities. So that is where we look at infinite integration limits. Basically, if you remember from our last lesson, we're concerned with trying to find the area when there's like a horizontal asymptote. We know that keep graphing it, it may get closer and closer to perhaps like the x-axis. So is there an actual answer for our integral or not? So in this particular case today, we're looking at not if it goes near a horizontal asymptote, but a vertical asymptote. So if you take a look at the diagram over here, okay, we can see that, for example, we have, I know you may not be able to read it, so I'm writing it, y equals 1 over the square root of x. So when x is equal to 0, there is going to be a vertical asymptote. Okay, so if you were asked to find the area under the curve from 0 to 1, are you going to actually be able to find it? So it's telling us in this particular case you can for these types of problems because we can evaluate it by doing the limit of the integral from a to 1 of our function with respect to x, as long as a is approaching 0 from the right, which should make sense in the diagram, okay, because we're coming from the right-hand side towards our vertical asymptote to figure out that area. And so, as you can see in this diagram, like if a approached 0 from the right, so it just kind of continued over, we're going to be able to evaluate this problem. So now that I explained all the diagrams, you can start copying the definition up here. So up here in like the white and yellow, you can see the definition. And I have to apologize that when I copied this image, I lost the capital I. So this should say improper integrals with infinite discontinuities. So you know that when there exists a vertical asymptote, we call it an infinite discontinuity. So it does deal with improper integrals. Number 1, if f is continuous on the interval from a to b, not including a but including b, we have this integral right here. I'm not sure if you can read that. I can clearly read that, so I'm going to make it perhaps a little bit bigger. Okay, so way to make it bigger there. Let's move on. So the integral of f of x with respect to x from a to b will equal the limit of the integral of f of x with respect to x from c to b. C would approach a from the right. So it's basically what I was describing in the diagram. Okay. So now let's talk about the other way. If f of x is continuous on the interval from a to b, including a, not b, then the integral of f of x with respect to x from a to b is equal to the limit of the integral of f of x with respect to x from a to c. C approaches b from the left, okay? So that means is that like where our vertical asymptote is, it's to the right of where we're plotting our points, as opposed to the last example. Our vertical asymptote was to the left. So kind of imagine something like this, and we needed to find the area. And last but not least, and then we'll get to 2 examples. If f of x is continuous on this interval, I'm sure you can copy it down, but you know what, I'll read it to you. From a to c including a not c, or from c to b not including c but including b. So somewhere there's like a vertical asymptote, and we're looking at from a to b, but our vertical asymptote was when like x is equal to c. Then what we need to do is split up our integral Let me see if I can move this other diagram. Hold on. Okay, and I did that so you can read it. It's the integral of f of x with respect to x from a to b is now two integrals. First, the integral of f of x with respect to x from a to c, and then we add it with our second integral, which is the integral of f of x with respect to x from c to b, which makes sense if you take a look at my quick diagram. All right, let's get to our examples. Okay, so our first example is exactly that situation in the last one I was trying to describe. Okay, so when x is equal to 1, we would have a vertical asymptote. We would have a vertical asymptote. Just make sure when you plug it back into the expression for the integrands, okay, you get a non-zero number over 0. And that's why I hesitated. You should always make sure that that's true. So there's a vertical asymptote. So that's how we're going to separate our integral in order to evaluate it. So this is going to equal to the integral from 0 to 1 of, we're going to rewrite this as x minus 1 to a power of negative 2/3. Okay, that'll be easier to work with respect to x, and the integral from 1, I almost said 0, sorry, making sure it looks like a 1, from 1 to 3, again, same integrands, just want to write it a little bit differently so we're able to evaluate. So here we go. Okay, I obviously lost my ink there, so let me rewrite that another time. Okay. We're still working on number 1. I am not sure what happened there. Hopefully we're all good. That's negative. Okay. All right. So for the first one, we're going to need the limit, okay, of 0 to c. And we have this expression here. My negatives are not coming out very well, so please bear with me as c approaches 1 from the left. And for this one, we have a different limit. Okay, so we have from c to 3 instead. And it's as c, it should come up as a c. There we go. Approaches 1 from the right. Okay, so now let's actually start evaluating. Okay, and we can use a u substitution, but you know, if it's like x or x minus 1 or x plus 2, it's going to work out very nicely. So if I add 1 to the numerator, if I add 1 to the exponent, I feel like I'm getting tired, so please bear with me. So we're going to get 1/3. So if I divide by 1/3, it's the same as 3. Okay. And I'm going to be plugging in c and 0. Okay, so same thing over here. Be careful of the notation. When I say same thing, I'm still getting 3x minus 1 and 1/3. I'm going to be plugging in 3 and c. So let me erase some of this and let me continue. So at this point, we're going to plug in c and 0, and then we're going to plug in 3 and c. So if I plug in c, I get this. If I plug in 0, I'm going to get negative 1 to the 1/3 power, which is negative 1. So I'd be subtracting a negative 3. So this is the same as adding 3. This is still c approaches 1 from the left. And let's do this one now. Make sure that's a plus sign. Okay. Now, I know I didn't show the substitution, so make sure that, you do show work, because if you make a little error, you want to show that you did know how to actually do this. So we're plugging in 3, and we get 2 to the 1/3 power, which is the same as the cubic root of 2. Okay, so once again, make sure, when it's possible and you have space, because I'm running out of space, you do show the work. And this is going to be 3c to the 1/3 power. Okay. I'm sorry, 3c minus 1. I don't know where I just got c by itself to the 1/3 power. Okay. So at this rate, I'm going to pause again to give myself more space. Okay, so usually at this point, we would plug in a value to see what we'd end up getting. So if we did plug in 1, we get 0 plus 3. So we end up with an answer of 3 here. And over here, if I did plug in 1, I would end up with 0 to the 1/3, and then this all becomes 0. So this answer may look a little complex, but we just evaluated number 1. Okay, so that is its answer. It is 3 plus 3 cubic root of 2. So now we're going to take a look at another problem. So if we take a look at number 2, we can tell that there would be a vertical asymptote when x is equal to 2. So how I would rewrite this would be equal to the integral from 1 to 2. You could write it like this, or you could just keep it as dx over x minus 2. But my lower limit here is 2, my upper limit here is 4. So now we're going to continue to write our limits. So this is going to be from 1 to c. As c approaches 2 from the left. And we're going to have, I forgot my limit. Here we go. The limit from c to 4, same expression, that's a d, as c approaches 2 from the right. So now, let's take a look at our first limit here. So if I were to evaluate this, we're going to get the ln absolute value of x minus 2. Okay, and then we're going to have to plug in c and 1. So same thing is going to go on over here, except we would be plugging in 4 and c. Okay. So let's continue up here because I ran out of space. If I plug in c, now I actually don't need the absolute value when I plug in c, because c would be greater than 1 and less than 4, or I should say like less than 2. But we'll just keep it in there for right now. And then I'm going to plug in 1. And the reason I kept it right now is because we're hopefully seeing a little bit of an issue here. So if you take a look at this right here, this is going to be the ln absolute value of -1. All right, you should know we're not going to be able to evaluate that. So I just want to take a look at what's happening, because we should end up with some sort of answer here. Okay, so hopefully I have space. We can rewrite this as the ln absolute value of c minus 2 over -1, which is the same And I need some space here. Okay. And I'm writing it, but it's just not appearing, which is the same as like the ln of 2 minus c. So what is going on here if we were to graph this in some way? So what you would be looking at, if let's say c is 0, okay, it's the ln of 2, so you can actually plug that in. You just, let's say this is like a c axis. You can plug in 2, you can't plug in 2. You get a vertical axis. You plug in 1, that's what I wanted to say, because the ln of 1 would be 0. Okay. And then we have ln of 2. Okay. And then we'd have, let's say we plug in -1, it's the ln of 3, which would be bigger than the ln of 2. So basically your graph would look like this. So as c is approaching 2 from the left, your values keep going down, 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 down. So we get an answer of -infinity. Okay? Once one of these answers becomes infinity or -infinity, you can't add with that. Infinity plus infinity, maybe to infinity, which is infinity. But at this point, we already know that there's no value or no solution. So we can't actually evaluate it. You would leave that as its answer. So in 1, it worked out very nice. We got a number out of it, but 2 didn't work out so nice. So this actually leads to our next lesson if we were to look to see if our function on that integral, from let's say 1 to 4, diverged or converged. That would help us out. So hopefully that next lesson will help you out so you know whether you get a value or not. So good luck with this lesson, and I will have the next one ready for you soon.